Hey, AP Statistics. So we're going into geometric random variables here at the end of section 6.3. This is another type of common random variable that we'll use. Another, and then the binomial distribution is another discrete random variable. The geometric's kind of similar, something that comes up a lot. Maybe not quite as much as binomial, but a frequent amount, and they'll use it on the test. So a geometric setting arises when we perform independent trials, so that's just like binomial, of the same chance process and record the number of trials that it takes to get one success. So I kind of mentioned this before. We're not interested in a fixed number of trials until we see how many successes we get. We're going to see how many trials until we get one success. So on each trial, the probability of success must be the same. So the geometric setting, we've got that. It's still got to be like binary, two outcomes. It's got to be independent, constant probability. But no longer are we interested in the fixed number of trials and how many successes. We're interested in how many trials it takes to get one success. So, and they're calling it y here. The number of trials that it takes is that it takes in a geometric setting is a geometric random variable. The probability distribution of y is a geometric distribution with a probability of p of success on any trial. The possible values are, so if you're interested in one success, you got to try at least once. Now our minimum is 1. With binomial, it was 0 because you could have 0 successes out of however many trials. Here, you got to at least try once in order to succeed. But it goes on and on and on forever. There's no technical end because you might, if you are independent setting, you might never eventually succeed. If you're trying to flip a coin until you get heads, theoretically it's possible that it would go on and on and on and on. It's extremely unlikely, but theoretically possible. So geometric probability is actually a little simpler than binomial. We can calculate it using this formula. Basically, if y is a geometric distribution with a probability p of success on each trial, the possible values are 1, 2, 3, so on and so forth. If k is any one of these values, so if I want to know what's the probability that it takes me exactly 5 tries to succeed, to flip a coin to get heads. Basically, what this amounts to is a bunch of failure. So there's a probability of failure. And then if I'm going to succeed on my 5th try, that means I'm going to have 4 failures followed up by 1 success. There's no arrangement. Your success always comes last when you're doing it, because once you have your success, you stop. You stop doing the thing that you're doing. All right, so for example, Mr. Lachel's class decides to play the Lucky Day game. A student will be selected at random from your class and asked to pick a day of the week, for example, Thursday. Then your teacher will use technology to randomly choose a day of the week as the lucky day. If the student picks the correct day, the class will have only one homework problem. If the student picks the wrong day, your teacher will select another student from the class at random and repeat the process. The game continues until a student correctly picks the lucky day. Let y equal the number of homework problems that the class receives. So you keep going until you have a success. Find the probability that the class receives exactly 10 homework problems as a result of playing the Lucky Day game. All right, so we have, in this case, a 1/7, or sorry, I guess, was it 1/7 or 1/5? All right, so it looks like it is 1/7. So I don't see anything about weekday provisions or anything like that. So basically what this amounts to is it's going to be a bunch of failure and then 9 failures and then a success. And we want to know what's the probability of that. And so y equals 10. So the way that we'll do this, and this one is screwed up if I remember correctly. Yeah, so let me just come back here and sketch it on. So what we'll do here is we'll take the probability of failure, which is going to be 6/7. Sorry, pretty crappy. So we're going to take 6/7 and then to the 9th power. So we're going to have 9 failures times 1/7. And that will be our calculation for having our first success on our 10th trial, and that's how many problems of homework we have. And so that's how you could type that in, whatever you get for that calculation. That's the number that we should have for that one. All right, so sorry, they're doing old news there. All right, so then the other question is, what's the probability that it will take less than 10 tries, that you'll have fewer than 10 homework problems? So this one they do actually kind of get right. So that could be anywhere from 1, you could have somebody gets right on the first try, second try, third try, fourth, all the way up to the 9th try, but not the 10th because we're going less than 10. And so the probability that you get on your first try is just a success, 1/7. And then a failure and a success would be the second try. 2 failures and a success. The 9th try would be 8 failures and a success. If you add all those up, you get 0.7503. So there's about a 75% chance that you'll get fewer than 10 homework problems by playing the lucky day game. Of course, we want to be able to do that in a calculator, and so here's how you do this in a calculator. Under that same second distribution where you found normal CDF and binomial PDF and CDF, you'll find Geomet PDF and CDF. And they work, and you could probably figure out how they work on your own. But you put in a couple of things. You have to put in the probability of success. There's no longer an N, a fixed number of trials. So you put the probability of success and the number of successes. PDF gives you equal to, CDF gives you less than or equal to, cumulative up to that point. And so CDF 9 would give you the probability up through there. And so the geometric distribution, geometric random variables do have a bit of an interesting shape if you look at those probabilities. It is a skewed right distribution. Each time we're multiplying by another failure, so that it just gets smaller. It's actually exponential decay is the shape that we're going to see there. And technically it goes on forever. So kind of an interesting shape to that distribution. Always will be skewed to the right. The mean and standard deviation, you've got the expected number of trials. These are pretty simple, and actually just the mean is all we need here. It's 1 over p. So if you think about it, it'll make sense. Like if I have a one half probability of success, that means I'm going to expect it to take me 2 tries to succeed. It could be more, it could be less, it could be in just 1, but it takes 2. If I have a 1/5 chance of success, if you do 1 over that probability, it ends up just being a 5. And so you would expect it to take you 5 times to get that 1 success. And so 1 over p is that expected value or that mean calculation for a binomial, for a geometric random variable.